Hey, this is Randy, and today is the introduction to polynomials. Let's do this thing. So right here, you can see that we have a roadmap, which shows what we're going to talk about today. So before we talk about the definition of a polynomial, let's talk about these three specific types of polynomials. We have the monomial, the binomial, and the trinomial. If we have some number like 6, that 6 by itself can function as a monomial. Now, if we do 6 times x, and remember this is really like saying x to the power of 1, or if we have some other exponent on x that is a whole number such as 4, we still have just a monomial. Now, if we say 6x to the 4th minus, we'll say 8x squared, we now have a binomial. So I'm going to highlight monomial right here and binomial. This is a binomial because it has two terms. So the first term is 6x to the 4th, and the second term is negative 8x squared. Okay, what about a trinomial? Well, a trinomial has three terms. So if we said, we'll say plus 3. We now have a trinomial, so I'm going to highlight trinomial. So the first term is 6x to the 4th, second term is negative 8x squared, and the third term is 3. Okay, now let's talk about what exactly is it that makes a polynomial, and what is it that makes something not a polynomial. So we'll read through this full definition, and then we'll talk about it piece by piece. A polynomial is the sum of a finite number of terms where each term has a coefficient being multiplied by a variable that is raised to a whole number power. Okay, so let's talk about that first part where it says a polynomial is the sum of a finite number of terms. Okay, well, this means that the number of terms cannot go on forever, right? There needs to be a defined amount of terms. In our example, we have 1, 2, 3 terms. Okay, so that part's pretty simple. Now it gets a little bit more interesting. Let me highlight right here. We're talking about the polynomial and its definition. And then pretty soon we'll talk about some examples of things that are not polynomials. Okay, so this next part of the definition says where each term has a coefficient being multiplied by a variable. Okay, so let's see if our example fulfills that part. So each term has a coefficient. We have term, term, terms. Let's see if each term has a coefficient, first of all. The coefficient here is 6. The coefficient here is negative 8. And the coefficient here is positive 3. Okay, and it says that the coefficient is being multiplied by a variable. Okay, so variable here we have is x, here we have x. Now, what's the variable right here? Well, some of you would maybe say there's no variable, but watch this. One way you can think about this is the following. So you could say 3 times x to the power of 0. Okay, so there's a variable in a sense because x to the power of 0 is the same as saying 1. Okay, anything to the power of 0 is 1. So in that sense, we still fulfill the definition because we have x to the power of 0 right there, next to what we call the constant term. Okay, the 3 is the constant term, but we'll talk more about that in a minute. Okay, cool. So that part of the definition is fulfilled. Now let's look at the last part. It says that variable, let me highlight right here, that variable is raised to a whole number power. Okay, what are the whole numbers? Now, there's a difference between integers and whole numbers. Integers include negatives and whole numbers don't. Okay. Also, integers and whole numbers do not include fractions or decimals. Okay, so the whole numbers, I'll just write it out right here. The whole numbers are 0, 1, 2, 3, and it goes on forever. Okay, those are whole numbers. So in that group of numbers is how whole numbers are defined, and that group of numbers is what our exponents need to be on the variables. Okay, so what I mean by that is, let me give you an example of something that would not fulfill that. So let me go to black here, and I'm going to erase these exponents. Now I'm going to put some exponents here that are not whole numbers. Okay, so we're going to say 2.1, 2.1. Why is 2.1 not a whole number? Because it's a decimal, right? And a whole number cannot be a decimal or a fraction. And if we go over here and we say 1/2, okay, well, there's a fraction. Once again, no good, because a fraction is not a whole number. So this expression right here would not be a polynomial because of those exponents right there. They disqualify it. Okay. In the same way, if you have a variable in the exponent, let's say that you have, we'll leave a 2 right there, and then right here we have a variable, we'll put x in the exponent. That variable also disqualifies this expression from being a polynomial, because that x, that black x, is not necessarily going to be a whole number. Okay, so there you go. Let's put those numbers back. Very good. And we can get rid of these highlights. And what I'm going to do now is I'm going to highlight this part, what is not a polynomial. We just talked about that. Okay, so we're almost finished. Real quick, let's talk about what is the leading coefficient in this situation. Well, it's the coefficient on the first term in the expression. In this case, the leading coefficient is 6. So we'll draw an arrow like that. There we go. Leading coefficient is 6. And if we have no coefficient, hypothetically, if I just had x, what would be the coefficient in this case? It would be 1, right? Because just saying x is like saying 1. Okay, so let's go back to 6 there. And I'm going to highlight leading coefficient. We just talked about that. And now, what is the degree of this expression? Well, the degree of the expression refers to the biggest exponent in the entire expression. Okay, so what's the biggest exponent here? It's 4, right? So this would be a 4th degree polynomial, or you can say that the polynomial has a degree of 4. Okay, now let me get rid of these exponents and we'll change things up a little bit, and then we'll talk about degree again. So let's say that we have a smaller exponent and then a bigger exponent. We'll go 7 right here. Okay, so now what is the degree of this expression? It's not 2, right? Because there's a bigger exponent than 2. The degree is 7, okay? Or you can say that it is a 7th degree polynomial. Okay, now what is the constant term? Let me highlight degree of expression here. Very good. What is the constant term? Well, the constant term was that number that was being multiplied by x to the power of 0. Remember how there's like an imaginary x to the power of 0 right here? That means that the constant term is 3, okay? There's the constant term. So let's highlight that part, and real quick, we'll talk about standard form. Let me get the highlighter here. There we go. Okay, so what is standard form of a polynomial? Well, in order for a polynomial to be in standard form, the exponents need to go in descending order from left to right. You'll notice that in this example, we have a 2, which is smaller than 7, and the 2 comes first. So this expression right now is not in standard form because we have a smaller and then a bigger exponent. So let's write an expression here that is in standard form. So if I erase the 2 right there, and I erase the 7, and then I put, we'll just change the expression. So I'm going to put a bigger exponent here. We'll just put 9. And then I put some smaller exponent. We'll put 3 right here. Now we have an expression that is a polynomial that is in standard form because the exponents go from bigger and then smaller. And then here it's like we have x to the power of 0, right? So even smaller. So now that they're going in descending order, the exponents, we have standard form. And one thing I'd like to clarify is that when we say expression, that's not equivalent to polynomial because expression is a more broad term and polynomial is more specifically defined than expression, which we can see right here. There's the definition that we just talked about. So let's highlight standard form here. And with that, we are finished with introduction to polynomials. And remember to always be clever.